Okay, good afternoon, everyone. So we have already seen context-free grammars and push-down automatas. So today, one part of Unit 4 which we had left was the equivalence between context-free grammars and push-down automatas. So context-free grammars are basically the grammars written for a group of language, that is context-free languages, and push-down automatas also are used as an acceptor or used to model this typical group of language, that is context-free language. This is similar to the equivalence between regular grammar, regular language, and finite automata. So we had seen interconversion between regular grammar and finite automata. We've seen how do we convert from a grammar to FA and FA to grammar. So we've seen right linear grammar, left linear grammar, if you remember. This is exactly similar to that, wherein we are going to see the equivalence between context-free grammars and push-down automatas. So today what we are going to study is how do we convert a context-free grammar to a push-down automata. Or we'll study that if you are given with a context-free grammar, how do we draw a push down automata from the given grammar. So one simple very simple thing that comes to my mind, okay, if I'm given a particular grammar, then one thing I can do is I can derive couple of strings from that grammar using sentential form or derivation tree form. And after I understand like what is the language that this particular grammar is generating, once if I understand the language, I can model with the help of push down automata. Okay, this is a very I can say naive or a brute force technique to do, but there is another way wherein you can using which you can convert a context free grammar to push down automata. Now what we see in this particular slide is a general two general rules that we follow to convert a grammar to PDA. Now if you look at this is basically representing your PDA, and your context free grammar basically has all these kind of production rules. So this is an in general rule which is written wherein how a production is converted to a transition on a PDA. Okay, so a production rule in a context free grammar will either have a series of non-terminal and terminals, or it will have only terminals into the on the right hand side. Right now here what we see, if for every terminal in your context free grammar, so your grammar is definitely going to have some terminals, so for every terminal symbol in your grammar we add one transition of this form. Now what is this? This is a transition which says that if A is on the input and if A is on the stack top, then this epsilon shows an operation of a, that it shows us pop operation on the stack. So for every terminal in the CFG, we are going to add this transition in our PDA. And for every non-terminal in our context-free grammar. So non-terminals are usually of this form. So capital A, which is a non-terminal on the left-hand side, produces some particular string is given here on the right-hand side. So whenever you encounter this kind of rule in your CFG, you add a production of this form. Now what is this saying? Without consuming anything from the input tape, if A is on the stack top, then replace this A with this string. So whatever is there on the left hand side, you have to assume that, okay, this is going to be there on the stack top, and if that is there on the top, we can replace this, or we can push all the things on the RHS of this production rule in the reverse order onto the stack. So this is A1 to AK, so we push from AK, then whatever it is, and then finally alpha 1. So alpha k to alpha 1 will be pushed onto the stack. So these are the two golden rules which we have to remember for conversion of CFG to PDA, and then likewise you can convert any CFG to PDA. Now let us look at this particular context-free grammar. Here there are three production rules. Capital A produces 0 A1, capital A produces B, and capital A produces hash. Now let us see if we can derive some string out of this particular grammar. So here capital A, which is the start symbol, can be replaced by 0 A1, and this A is again from this A we again derive 00 A11, and then this A is replaced with B using this particular rule, and then finally this B is replaced with the terminal hash. So finally this is just one of the strings which is derived from the grammar of this particular language. So if we pick up this particular string and using these two general rules which we saw, we'll try to simulate the PDA on this string. So whatever PDA that you are going to actually create or design should accept this string, because this string is derived from the grammar, and now you're going to actually so whatever PDA you draw should actually accept this string. So we'll just see the control of the PDA in the next slide. Now what is the step one in this conversion? So if I am actually looking at this grammar, I see that A is my start symbol. So at the first place, your start symbol should be pushed onto your stack always. Okay, so if I don't push my stack symbol on the stack, until then I can never replace this with some string on the right hand side. So if you go back here, you have to replace this A with its string on the RHS. So what is the production that we add is, without consuming anything from the input, if A is on the stack top, then replace it with or push all these things onto the stack. So that is what is shown here. So we added this particular transition, that without consuming anything from the input or without doing anything on the stack, first push A on this particular sign, which is actually denoting the bottom of the stack. So we have first initially pushed the start symbol, and this is the string on the tape on which the PDA is also going to be executing. Okay, so we are going to simulate the run of the PDA on this particular tape. Now next is this A should be this A on the stack top should be replaced by 1, A and 0. So we have to eventually push this. So in order to push this, what transition should be there on the PDA? So without consuming again any input from the input tape, if A is there on the stack top, then push these things on the stack. So push these three symbols on the stack. So that is what is now done with the help of this transition. So if you want this to be the content of the stack, we should have this kind of rule or this kind of transition on your PDA. Okay, now I'm trying to explain you why we need this. Now we need this particular contents of the stack, because if there is a match between the stack top and the symbol under the tape head on the input, then we can actually pop. Okay, and if eventually likewise if we keep on popping, we may enter into a state wherein there is nothing on the stack and even the string is completely been read, and now the tape head is on the epsilon. If that is the condition, then we are going to actually accept the string. So the PAD has to accept the string. So after this, what will happen? I want my 0 to be matched with this 0, okay, and this 0 should be popped off the stack. So what will be the corresponding transition that I should add on to the PDA for this particular action to happen? If there is a 0 on the input and if there is a 0 on the stack top, then perform a pop operation. Now that will be the third transition that you add to your PDA. So that is what is given here. If there is 0 on the input tape and 0 on the stack top, perform a pop. So now we have performed pop operation, and this is the content of the stack and this is the content of the input. Now, in order to accept again this input by a stack, what is the next step that we should do? In this simulation, I should again replace this A with these three things. So eventually I want this to be pushed onto the stack. So again, using this production rule, these three things will go onto the stack in the reverse order. So again, using this rule, which we had previously also used, we are going to push one A0 onto the stack. And then again, using this rule, we are going to pop the content, we are going to pop the element on the top of the stack, that is 0, and we are going to match it with the symbol under the tape head. So likewise, we keep on replacing the non-terminals by pushing their whatever is the string, production string written on the RHS of the particular production rule, and whenever there is a terminal symbol in your context free grammar, for every terminal we should have a rule like this, wherein if there is a terminal on the top of the stack and the same terminal is there under the tape head on the input tape, we have to perform a pop operation. Now, if you look at this complete run, again this A, in order to now match this A with hash, we should use the third rule, right? So we should replace this A with B now. So this A has to be replaced with B. In order to do this, I should have some transition on my PDA, right? So whenever there is a non-terminal symbol in your production rule, what kind of transition you add to your PDA without consuming any input from the tape? If there is an A on the top of the stack, then replace it with the contents on the RHS in the production rule. So we have added this particular rule in our PDA. So, and we see that why we need to do it. Okay. So here, after replacing this B, if I want to match it with hash, what I need this B to be replaced by this particular hash. So what kind of production I need on my PDA? Again, without consuming anything, if there is a non-terminal B in your CFG, you push the right hand side contents onto the stack. So we bring a hash here. So now in this case, now if B is, so using this particular transition, we replace this B with hash, okay? And then if both hash is there on the tape head and hash is there on the stack top, we need to perform a pop. Now, because hash is again a terminal symbol, we are going to add this particular transition where hash is on the tape and hash is on the stack top, perform a pop. Similarly, after this hash is also being consumed, or now the tape head is pointing to 1, we need a production of this form. If 1 is on the tape and 1 is on the stack top, again pop. So likewise, the entire string will be completely scanned, and finally the content of the stack will be nothing but the stack bottom symbol, which denotes that the stack is empty. So from all of this, what we see is there are typical rules that we can generalize the process with is whenever there is a non-terminal in a grammar, for every non-terminal, you add this kind of production in your, this kind of transition in your PDA, wherein you do not consume anything from the input. So the tape head is not going to move ahead. The tape head remains in the same position. And for that particular capital A on the stack top, we push whatever is there on the right hand side of the production rule to the stack in the reverse method. So for this, again, for this particular production, we have added this rule. For this production, we have added this rule. So we simply push this on the stack, and we write here these non-terminals to be present at the top of the stack. And for every terminal, we add this kind of production. So here we had three terminals, 0, 1, and hash. So in this case, we added three typical transitions in your PDA. For each of the terminals, we perform a pop operation. And finally, so basically your PDA has only one state, and after this, epsilon is there on the input tape, and your stack bottom symbol is there on the stack, and epsilon will be again. So you do nothing basically. This shows that you do nothing with your PDA. You push back that epsilon onto the PDA, and the machine enters into the final state. Now here, these are the rules to convert a CFG to PDA. So these rules I already narrated. Now one thing we have to take care of is all these two general rules are applicable if and only if the context-free grammar is in a Greeback normal form. So for any grammar, first, to convert that grammar to PDA, you have to first rewrite that CFG into a typical normal form, that is GNF form. And then once you convert the grammar to GNF, after that you try to apply these two rules, and then the second step says that the PDA will have only one state Q, which we saw here previously. So only on this one single state, you put all these transition using the two rules that we have seen. Any questions? Okay, so we'll see one more example. Now the question says convert the following grammar to PDA that accepts this particular language denoted by this grammar. Now looking at this grammar, first thing that you have to find out is whether it is in GNF form or not. If you remember, we studied two normal forms. One is Chomsky normal form and another one was Greeback normal form. So what is Greeback normal form? So in your Greeback normal form, all your production rules should be of this form, wherein a non-terminal produces a terminal, or a non-terminal produces a terminal followed by one or more non-terminals. So here it can have either one non-terminal or it can have one or more non-terminal. Can have one or more non-terminals followed by a terminal. So all of these are examples of productions in GNF form. Okay. Now here capital A is a non-terminal, B, N, G, H, J, all are non-terminals, H, G, all are not. Everything written in capital is non-terminal. So compulsorily your grammar should be in this particular form to apply those two rules. So any grammar which is not in this form, first you have to bring in GNF form. If you remember from my previous classes, we studied that in order to bring the grammar in a normal form, first you have to again simplify the grammar. And we studied three steps in simplification of grammar: elimination of unit symbols, removal of non-generating, non-reachable symbol, all those things. So first the grammar has to be simplified, then it has to be brought into a GNF form, and then you apply the two rules to design the PDA. Now, first is we have this, we can see this unit production. Okay, S produces capital A is a unit production. So first is we'll simplify this grammar by eliminating unit production, and then we'll bring it to GNF form. So how do we eliminate the unit production? We simply expand this A with all of these things mentioned in this particular production rule. So S produces 0S1, or it produces 1A0 or capital. So S will go off from here and then epsilon. So S produces 0S1, 1S0 and epsilon. Now this particular grammar is a simplified version which is not in GNF form. So we have to bring it in GNF form. Why it is not in GNF form? Because after this particular non-terminal, we can see a terminal. So this is not allowed in GNF form. A terminal has to be followed by one or more non-terminals. So what we can do is we can replace this 1 with X, 0 with Y, and we can add two more production rules in our CFG, that is X produces, capital X produces 1 and capital Y produces 0. So we just rewrite the grammar to bring it to this particular GNF form. And after we have rewritten this grammar, now we have to think of our PDA. Now, if you look at this particular CFG, how many terminals we see, how many non-terminals we see. Depending on that, we have those many number of transitions in our PDA. So if you look here, now these are all the transitions of the PDA. So what we observe, the first thing is we have to push the start symbol onto the stack. Okay, now start symbol is also non-terminal. So for non-terminal, what kind of transition should be there? Without consuming any input, we have to push, if that particular non-terminal is there on the stack top, then push all the elements on the RHS of the production rule. So first step is push. You write a transition, you should have a transition or an ID which is actually pushing the start symbol onto the stack, and after that for every non-terminal you have to add the transitions. So this particular step says that without consuming anything from the input, if S is there on the stack top, then what all to be done? So the machine remains in the state Q only, and we replace this S on the stack top with 0SX, 1SY and epsilon. Now this is what is coming from this particular simplified GNF grammar. Okay, so if S is there on the stack top and without consuming any input, we push these things onto the stack. So we have three transitions in the PDA with respect to this particular start symbol S. So that is what is shown here. Either this happens or this happens or this happens. Similarly, we have to add for X produces 1. So what kind of rule will be there? Without consuming anything from the tape, if capital is X is there on the stack top, then we have to push whatever is there on the RHS of this particular non-terminal. So RHS we have 1, so we push 1. Similarly, we add a rule for this. Without consuming anything from the input, if Y is there on the top of the stack, then we add this rule that we are going to push 0. We replace this Y with 0. Again, for every terminal, we add a pop operation. So if 0 is there on the input tape, 0 is there on the stack top, perform pop. Similarly for 1, and then we stop. So this is the representation of our PDA. Along with this, you have to describe your PDA also, okay, with the help of all the components that you studied: Q, final state, the stack bottom symbol and everything. These are just the description of the transitions in the PDA. The last example is this one. Now construct the PDA for this grammar where S produces 0BB, B produces 0S or 1S or 0. Now first check whether this is in GNF form. I see that the first rule is in the GNF form because one terminal is followed by one or more non-terminal acceptable. Even this is in GNF form, this is in GNF form, and this rule is in GNF form. So now we can directly start writing the transitions of our PDA. So what will be the first transition? Pick up the non-terminals and add this kind of transition. So without consuming any input, S, push 0 VB. For first rule, we have this particular transition. Now for this second production rule, so here we have three production rules, 1, 2, and 3. So for this one, we are going to push 0s onto the stack. So without consuming again anything from the input, so you denote it by an epsilon. If B is on the top, push 0s or 1s or 0. And we have two terminals, 0 and 1. So again, for them, you have to write the pop operations. So this completes understanding of how do we convert a context-free grammar to a PDA. If you have any questions, you can ask. So,
Ma'am,
yes.
I'm not able to understand whether a GNF, whether a CFG is a GNF or it is not GNF.
Okay, so you have to actually go back and understand what is first a normal form. Okay, a normal form is nothing but formatting a grammar in a very simple language. Whenever you write something in your text editor, okay, you write some text, okay, and then you format that text. So you format it with, say, Times New Roman with a size of 12, and then you make it bold. So what we are doing is, for the same text which represents same semantics, same world knowledge, we just format it. Okay. Similarly, grammar can be rewritten in some form. Now there are two. So these are two standard forms. Okay. So any grammar can be converted to these two standard forms. Now, these two standard forms were invented for the purpose of uniformity and for bringing some standardization in writing grammars. Fine. Now, given grammar, so first form was the Chomsky's normal form, and the second one is a Greback normal form. For this conversion, we need GNF form. Now, GNF form is a typical format where each production has to follow these two things, what the ones which I mentioned. So here in this case, every production should be of this form, where on the RHS you should have a terminal symbol. Either S produces a terminal, okay, that is a B produces 0. Now here in this production rule, capital B produces 0, 0 is a terminal. Okay, so this is a valid form. This is valid in GNF. Again, another thing which is valid is a non-terminal produces terminal, a single terminal followed by one or more non-terminals. So if you look at this rule, here we have a non-terminal B produces a single terminal followed by
Non-terminal.
a single non-terminal. So even this is valid. Here a terminal is followed by two non-terminal. Even this is valid. So GNF says कि there can be one or more non-terminals. लेकिन शुरुआत होनी चाहिए हमेशा एक terminals के साथ. ठीक है? या तो फिर either you have only one terminal, or if you want to have non-terminals, necessarily उसके पहले एक terminal होना चाहिए. If you look at the previous one here, this is not in GNF form, because we had one terminal, uske baad there is one non-terminal, and then we again have a terminal, which is not allowed. So for this, we had rewritten this by replacing this one with capital X. We created another non-terminal. We created an capital X here, and then we added one additional production rule. Capital X produces 1. So we replaced this one with capital X, and then we had to add another rule to bring it to a GNF form. Is this clear now?
Yes, ma'am.
Okay. Any other question? Fine. So have you all